Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video I'm going to talk about an infinitely repeated prisoner's dilemma. Specifically, we're going to be returning to the pricing version of the prisoner's dilemma, which we introduced back in the game theory videos. To do a quick review of that game, using the normal form game matrix, we had two firms which each had two possible actions. Firm 1 and Firm 2. The two possible actions they could choose were to price their good at $2 or at $4. This game follows the general rules of the Bertrand model, where if the prices are the same, the two firms split the market, but if one prices under the other, they take the entire market. If both price at $2, they each make a profit of $60. If they each price at $4, they each make a profit of $80. If Firm 1 undercuts Firm 2, then they get a profit of $120, while Firm 2 gets nothing. And if the opposite happens, and Firm 2 undercuts Firm 1, they get $120 profit, and Firm 1 gets nothing. I covered the derivation of these numbers back in the game theory videos. Choosing a price of $2 is the dominant strategy here. No matter what the other firm picks, each individual firm always makes more profit by choosing $2. This leaves both firms with a profit of $60. However, had both firms priced at $4, then they would have both done better and gotten a profit of $80. Unfortunately for them, individual greed gets in the way, and that outcome is not sustainable as a Nash equilibrium. As long as we have a one-shot version of the game, that is, that it only occurs once, there's no way to achieve this cooperative outcome. In order to find a possible outcome where the firms cooperate, we need to extend the model. We are now going to consider an infinitely repeated version of this game. The game we've just outlined is called the stage game. The game as a whole consists of playing this stage game over and over and over an infinite number of times. In each time period, the two firms simultaneously choose prices, they find out what happens and collect their profits, and then we move on to the next period, and it all repeats over again, with the firms collecting profits at each time period. In determining their actions, the players take their future profits into account, but they discount them according to present value. Future profits are worth something, but not as much as profits right now. In real life, businesses often do interact with their rivals over and over and over through time, so arguably, repeated games are a more accurate representation of what really goes on. Now that we have a repeated game environment, we have a much wider strategy set available to our players. It's not just, should I choose $2 or should I choose $4? Strategies can still be simple like that, as in the one-shot game, and in fact, both firms choosing $2 for the rest of eternity is still a Nash equilibrium, but it's no longer the only Nash equilibrium. To find a potentially cooperative Nash equilibrium, we need to think about strategies that condition on what happened in the past, which is something that's possible now that we have a repeated game. Consider a new strategy called the Grim Trigger strategy. Grim Trigger has three parts. Number 1, in the initial period, which we call t equals 0, play the cooperative action. In the pricing game we've been talking about, that involves charging the high price of $4, but in the classic prisoner's dilemma, this is staying silent. Number 2, in any subsequent period, that is t greater than or equal to 1, play the cooperative action if the other player cooperated in all previous periods. Part 3, in any subsequent period, again, t greater than or equal to 1, play the hostile action, that is charging the low price of $2 in the pricing game, or Fink in the prisoner's dilemma, if the other player has ever played the hostile action in any previous period. The idea here is to start out cooperating and continue cooperating as long as the other player continues to cooperate. But if the other player ever betrays your trust, that trust is lost forever, and we punish them for the rest of eternity by playing the hostile action forever. This is where the term Grim Trigger comes from. The other player playing the hostile action pulls the trigger on the punishment, which continues forever. Since players care about the future, they might choose to not pull the trigger and continue cooperating forever. The Grim Trigger strategy can support a cooperative Nash equilibrium if, while both players use the Grim Trigger strategy, Neither player can improve their payoff by switching to another strategy. This is basically the same idea that we've engaged with Nash equilibrium in the past. Switching to another strategy, hence breaking cooperation, is called defection. And so to figure out if we can have a Nash equilibrium using Grim Trigger, we need to figure out what is the payoff for following the Grim Trigger strategy, and what is the payoff from defection. If defection is better, then the Grim Trigger strategy cannot support a cooperative Nash equilibrium. Let's go through the Grim Trigger strategy specifically for our pricing game. Number 1. In the initial period, set the price at $4. Number 2. In any subsequent period, set a price of $4 if the other firm has also priced at $4 in all previous periods. And number 3. In any subsequent period, set the price at $2 if the other firm has ever priced at $2 in any previous period. Let's now see if both firms using Grim Trigger is a Nash equilibrium. The notation we're going to use is each time period is designated with T. T is just a generic time period that can be 0, 1, 2, 3, all the way out to infinity. T equals 0 is the initial period. Think of that as right now, 0 periods into the future. If both players are playing Grim Trigger, then they're both going to start by playing the cooperative action of pricing at $4. This is going to give both firms a profit of 80. If both firms continue playing Grim Trigger, then they're going to get pi 1 is 80, pi 2 is 80, and so on forever. From the perspective of right now, or period 0, though, we have to discount those future profits. I am going to use a big pi to denote the present value of the entire profit stream. And I'm going to put Grim here to indicate that we are playing the Grim Trigger strategy. We're going to get 80 initially, then we're going to get 80 over 1 plus r, then we're going to get 80 over 1 plus r squared, and so on forever. Using the formula for the geometric series that we talked about before, this part has a convenient formula, and we can rewrite this whole thing as 80 plus 80 over r. If we knew the interest rate, we could just plug that in to calculate the present value. Now let's think about what would happen if a firm were to defect. Remember, we are assuming the other player is still playing Grim Trigger, and so they are going to initially still attempt to cooperate at $4. But instead, we are going to defect and choose $2. If we decide to defect, then we're going to get a big burst of profit in period 0 of 120. But now the trigger has been pulled, and so the other firm playing Grim Trigger is always going to pick $2 from here on out. And so the best response to that is just to also continue to price at $2, therefore making a profit in the next period of 60, and so on forever. We're again going to use a big pi, but I'll put DEF to denote defection. We get the initial 120, but then we get 60 over 1 plus r in period 1, and then 60 over 1 plus r squared, and then that continues forever. We're again going to use our geometric series formula here to rewrite this as 120 plus 60 over r. We now need to compare the present value from defection with the present value for playing Grim Trigger. Both players using Grim Trigger is a Nash equilibrium if the present value of the whole game for playing Grim Trigger is greater than or equal to the present value of the entire game when we defect. If we compare these two, we can see that Grim Trigger gives us a nice constant profit of 80 forever, whereas defection gives us an initial big burst of profit, but then a lower amount of profit into the future. So looking at these, we're not sure which one is better. Let's plug them in to find out. The Grim Trigger present value is 80 plus 80 over r, which needs to be greater than or equal to 120 plus 60 over r. Now we do some algebra here. I'm going to subtract 80 from both sides, and that's going to give me 40. And then on the left-hand side, 80 over r minus 60 over r is 20 over r. If I multiply both sides by r, I get 20 greater than or equal to 40 r. 20 divided by 40 is 1/2. Just for convenience, I'm going to flip this whole thing around and write this as r less than or equal to 1/2. And so this tells us that as long as the interest rate is below 50%, then this particular game can have a cooperative Nash equilibrium with everyone using the Grim Trigger strategy. Note that this answer depends on the specific game we're doing. Other games with different payoffs might have a different condition on the interest rate. We've essentially determined an upper limit on the interest rate for it to be possible to have a cooperative Nash equilibrium using Grim Trigger. That is not necessarily to say that this cooperative outcome will happen, it's saying that it's possible to happen. Remember that everybody picking $2 forever is also still a possible Nash equilibrium. What this tells us is that when interest rates are low, it's easier to cooperate, but high interest rates make it impossible to cooperate. And this is pretty intuitive if we think about it. High interest rates make it so that getting profit in the future is worth relatively less because you're missing out on all that interest. And so when interest rates are high, people are more impatient to get profits now as opposed to later. That's going to make that big burst of profit of 120 right away from defecting much more attractive than getting the nice steady 80 forever. But when interest rates are low, then future profit is not so bad compared to current profit, and so the firms would be much more willing to accept a little bit less now in exchange for more in the future. So far, we've only thought about a game with 2 players. When we have lots of firms, it's more difficult to cooperate, or collude as we say, because the potential upside for defecting is even better. Here we had one firm who's taking the entire market from the one other firm, but imagine if we had 10 firms, we now have one firm whose share of the market is relatively small, potentially taking the entire market when they defect, and that's a much bigger temptation. From a practical standpoint, maintaining collusion over a large number of firms is also more difficult because firms have to keep an eye on each other and monitor each other to see if anybody is defecting. Now that we've covered a repeated version of a basic Prisoner's Dilemma style game, in the next video we're going to be ready to move on and apply these concepts to the Cournot model.